Hi, I'm Ryan Baker, and this is Big Day in Education. Today we start the second week of our class with a continuation of our discussion of prediction models and classifiers in specific. Today we're going to talk about detector, or classifier in general, confidence. Let's quickly reconsider classification. As you may remember, in classification, there's something you want to predict called the label or the predicted variable, and that something is categorical. Now, it can be useful when you're classifying to know yes or no, to get an answer yes or no to a question. For example, let's say you go to the Ptarmigan's disease detector, and the detector says you don't have Ptarmigan's disease. Now you can throw a big party and be happy. But it's even more useful to know how certain the prediction is. Let's say that the detector says that there's a 50.1% chance that you don't have Ptarmigan's disease. Are you still celebrating? Not once you know the confidence. That's why confidences matter. You can use detector confidences in several ways. First of all, for gradated intervention. Maybe you want to give a strong intervention if the confidence is high, over 60% or 70% or whatever. Maybe you want to give no intervention at all if the confidence is under 40%. And maybe you want to give some sort of fail-soft intervention, an intervention that's just not that harmful if you give it incorrectly if the confidence is in between. Now, these decisions about the strength of intervention can be made based on a cost-benefit analysis. You have to ask, what's the cost of an incorrectly applied intervention compared to what's the benefit of a correctly applied intervention? Let's look at an example. Let's say that an incorrectly applied intervention will cost the student 1 minute of time. So there's no cost to learning, it doesn't drive the student away, but the student loses a minute of their time. And each minute, the student is typically going to learn 0.05% of course content. So there's a real cost to losing that time. A correctly applied intervention will result in the student learning 0.03% more course content than they would have learned otherwise. In that case, we can compute the expected value of the intervention based on an equation of 0.03 times confidence minus 0.05 times 1 minus confidence. So in other words, if you're right, you have an expected value of 0.03, but if you're wrong, you have a negative expected value of 0.05. And here we can see this graph plotted on this function plotted on the graph. So we can see that if detector confidence is about 62%, then it's good. So let's consider the expected value of the intervention based on these parameters, knowing how good that's going to be if the intervention works and how bad it's going to be if the intervention doesn't work. And we can actually plot a function on this. And we see that the expected gain comes above 0 when the confidence is about at 61% or so. What if we had a second intervention? This intervention is stronger, but it's also more harmful if it's wrongly applied. So if it's correctly applied, then you're going to get a boost of 0.05, but if it's incorrectly applied, you're going to lose 0.08. In this case, you can see that you can plot a second line, the orange line, and see where the two lines intersect. So what you can say from this is that there's a certain range where the weaker of the two interventions starts to work, where it comes above 0, and it's better than the stronger of the two interventions. That's the fail-soft range. In this case, between about 62% and about 75%. Above 75%, you want to use the stronger intervention. So by doing this type of cost-benefit analysis, you get an idea of where you want to apply interventions. And it isn't always just at 50%. There's this kind of idea, 50% is where you're right. But in fact, you should look at the actual cost and benefit of an intervention when you decide when to use an intervention. 50% is often not the right place to actually make a decision. Let's discuss a second use of detector confidence. Discovery of models analyses. You take your model, and then you use your model in further analyses. We're going to discuss this later in the course. But the big idea is you want to use confidence rather than just yes, no, rather than just if you're 50% or above 1, if you're 50% or below 0, because you keep more information when you use confidence. If you take a student who is 60% confident that he's bored, and a student who's 40% confident that he's bored every time, kind of on the average, you don't want to just treat the first student as always 1 and the second student as always 0. You'll be magnifying the apparent difference between the two students. Now, confidences are not always available. Not all classifiers provide confidence estimates. Some, like step regression, provide pseudo-confidences, estimates of how strong the prediction is that don't scale nicely from 0 to 1. These still show relative strength that can be used in comparing two predictions to each other. They're still worth keeping and thinking about. Some algorithms give it to you in a straightforward fashion. They just say, my confidence for this decision is 72%. With others, you need to parse it out of the software output, which really is pretty straightforward. take decision trees like J48. In RapidMiner, it'll show you output that looks like this, and you can actually compute confidences out of it. So what you do is you take confidence equals yes divided by yes plus no. So in this case, confidence is 2 divided by 2 plus 1, which those of you who have taken elementary school mathematics should be able to apply your order of operations and say, gee, that's 66.67%. On the top, you actually see a case where there's 100% confidence. And that doesn't truly mean that there's a 100% chance this is right. It just means that within the data, the model can infer that there's 100% confidence. So always take these with just a little bit of salt, because they're always based on the data that you actually had. This case below, you see that there was only one case where it was right and 44 cases where it was wrong. So this model has a confidence of 2.2% that the answer is yes. But really the way to think about this is it's no with 97.88%. Another thing worth thinking about is that confidences can be lumpy in the way the detectors present them. What I mean by that is the previous tree only had 4 values: 100%, 66.67%, 50%, and 2.22%. This isn't a problem per se. It's okay to have lumpy confidence, but some implementations of standard metrics, like A prime, can behave oddly in this case, and we'll discuss this later in the week. And by the way, I should say that lumpy confidence is common in tree and rule-based classifiers. It's almost always a good idea to use confidence when it's available, but not all metrics use this, and we'll discuss this later this week.
Another important metric is risk ratio. It's not available through all tools, but where you can find it, it's a good way of analyzing the impact of specific predictors on your prediction. It's used with binary predictors. So take a predictor P. The risk ratio is the probability when P is 1 divided by the probability when P is 0. To give an example, let's say that students who get into 3 or more fights in school have a 20% chance of dropping out, whereas students who don't get into 3 or more fights in school have a 5% chance of dropping out. In that case, our risk ratio is the probability when 3 fights is 1 over the probability when 3 fights is 0, or 0.2 over 0.05, or in other words, 4. So the risk ratio for 3 fights or more is 4. You're 4 times more likely to drop out if you get into 3 or more fights in school. Now, if you've got a numerical predictor, you can turn it into a binary predictor with a threshold, like in our last example. Risk ratio is a really nice metric because it's a clear way to communicate the effects of a variable on your predicted outcome.
So thank you for coming to today's lecture on confidence. I hope you found it interesting, and I'll see you in the forums. See you next time.